Welcome. In this session, we'll continue with the discussion on Z transform, and in this very session, we'll see how to solve a difference equation using Z transform. Now, first of all, what's a difference equation? Now, a difference equation is an analog of a differential equation. So, a difference equation is an analog of a differential equation for discrete time systems. We know a differential equation describes or characterizes a continuous time system. Same way, difference equation characterizes or describes a discrete time system. So, in other words, we write the input-output relationship of a discrete time system by one more way, and that's referred as the difference equation. Now, the nth order difference equation, we can write it like this. Nth order difference equation can be written like this. K is running from A to N, A K y of n minus k summation j running from 0 to m, aj, sorry, not aj, this is different. This is bj x of n minus j. So this is a difference equation, nth order difference equation if n is greater than m. And we say y is the output, x is the input of the system, and this is the nth order difference equation. Now, if I expand this difference equation like this, I can write it a0 y of n minus 0, so that's simply n, so it will be left with y of n. Then I can write the summation as it is 1, so I am only taking k equal to 0 point outside from this. It will be ak y of n minus k. Then on right side I have j running from 0 to m, dj x of n minus j. So this is the nth order difference equation, and this difference equation characterizes a discrete time system. So this is a difference equation. Now, taking the Z transform of this equation on both sides. So taking the Z transform of this equation on both sides, what we'll get? So this is k equal to k y of n minus k, and this will be Z transform of j running from 0 to n, dj x of n minus j. So this is the Z transform, that's on the both sides. Now, using the linearity property of Z transform, we can write it as, we can write the left hand side as like this. So Z transform of sum of two terms is the Z transform of the individual term. So we can write, I'm taking the Z transform inside. You can say bj is a constant. This is the Z transform. Now, if I take a naught outside, this will be simply a naught Z transform of y of n. And again, if I use the linearity property here, I can write it and take the coefficient outside ak. This will be Z transform of y of n minus k. This is the Z transform of j running from 0 to m, bj Z transform of x of n minus j. Now, if I say Z transform of y of n is y of z, so Z transform of y of n is y of z, and assuming this, so Z transform of, what will be the Z transform of y of n minus k? Using the shifting property, you say this is Z transform, this will be simply y of z. So use capital notation. So this is y of z. So if z transform y of n is y of z, then z transform of y of n minus k is 0 is power minus k y of z. This is using the shifting property. This is by using shifting property of z transform. So this is by using shifting property. So then z transform of bj, and let's suppose the z transform of x of n is x of z, then z transform of this will be x of n minus j is j, 0 is power minus j x of z. Now taking y of z common on this side, this will be a naught plus summation k running from 1 to n ak 0 is power minus k. This will be summation j running from 0 to n bj 0 is power minus j, and if I write x of z like this. So this is the z transform of this differentiation. Now if I write yz, which is the output, by xz, dividing both sides by xz, and if I transfer this on the right hand side, so this I can write as 0 from 0 to n bj 0 is power minus j divided by a naught plus summation k running from 1 to n ak 0 is power minus k. So what's output by input for the x output by input is referred as the transfer function of the system. So the transfer function from this difference equation, you can write it summation j running from 0 to n bj 0 to minus j u naught plus summation k running from 1 to n ak minus 0 to minus k. So this is the summation, and this is the transfer function of the system whose difference equation is this. So which is described by this difference equation. So this is the transfer function of the system. This is the transfer function of the system. So this is the transfer function of z. Now remember, if you are able to obtain the transfer function, if you are able to obtain y of z, if you are able to obtain y of z from this difference equation, you can write it as this is y of z by x of z. So from this, if we have this, we can compute the output of this system, which is described by this another difference equation for any input. Substitute the z transform of the input and multiplying it with this transfer function, we can compute the output for any input. So using this, so once you have derived the transfer function of this this difference equation, then we can compute the output for any input of this. Let me show you the example to illustrate this. Let's suppose we have a difference equation which is like this: y of n is 1 by 2 y of n minus 1 plus twice x of n. So this is the difference equation. So this is a difference equation of order 1. Remember, this is a difference equation of order 1. So to solve this difference equation, take z transform on both sides. So if I take the z transform on both sides, first I will obtain the transfer function of the system. Plus 2 x of n. And using the linearity property of z transform, if I say z transform of y of n is y of z, so I can write it like this. So using the linearity property here, it will be 1 by 2 z transform of y of n minus 1 plus z transform of plus x of n. So using the linearity property, this will be 1 by 2, and z transform of y of n is y of z, then z transform of y of n minus 1 is z minus 1 y of z. This will be twice, and let's say the z transform of x of n is x of z. Now transferring this term on the left hand side, we'll write it as y of z minus 1 by 2 z inverse y of z, and this is 2 x of z. Now So this is this plus z. Now taking y of z common, we can write it as 1 minus 1 by 2 z inverse is equal to x of z. Now we can write it as y of z divided by x of z, and transferring this term on the right hand side, we can write it as 1 by 2 z inverse. So this is h of z. So h of z is simply 1 by 1 minus 2 z. So this is the transfer function of the system. Now the impulse response of the system. Now how do we calculate the impulse response? Whose transfer function is this? You can simply take the inverse transform of this. That will give you the transfer function. But let me illustrate it from here. Let me illustrate it using this. So let me illustrate it using this. We know to calculate the impulse response. So to calculate the impulse response of this system, we know why h of z is y of z means output by input. So output will be simply h of z, x of z. Now to calculate the impulse response, means the input is x of n is delta n. So what's the z transform of x of n? Delta n, 1. We already computed this. So multiplying it with 1, so it will be h of z. That's why I said take the inverse z transform of this directly. So this will be 1 by 2 inverse, and taking the inverse z transform of this, we have y raised by n, and you can say this is 1 by 2 n n. If you assume this is the z transform of this, if you assume this is the z transform of 1 minus a z inverse, and region of convergence is, and region of convergence is greater than f. You can also say this is equal to actually minus 2 1 by 2 raised by n u of minus a minus 1 if you assume the region of convergence is, instead of a, by the way, you have here 1 by 2. So instead of a, you have 1 by 2 here, and we can say this is equal to when we assume that this is the z transform of this. Z transform of this is equal to 1 by 1 minus a z inverse. This is a z inverse when then this is the z transform. If I am assuming the region of convergence is less than a, and here a is 1 by 2. So if I say, I can say this is also equal to this. So based on which one you assume, and this is actually we should use this one. Why? Because this will give you the causal system, and this will assume that the system is causal, and this one will assume that the system is non-causal system. So that's the difference. You can now for the same system which is described by this difference equation, which is described by the same difference equation. If I have to compute now the step response, means my x of n is now u of n. So x of n is u of n. Using the z transform, how do I compute this? See, I have already computed h of z for this. H of z is 2 divided by 1 by 1 minus 2 z inverse. Now, what is x of z here? We know x of z is 1 by 1 minus 1 by 1 minus z inverse, and this is this is we have already computed the z transform of u of n, if you remember. So we can compute y of z, which can be written as h of z, x of z. So we can compute the output by doing this multiplication. X of z is already computed for this example, and x of z is 1 by 1 minus z inverse. Now we can compute the output of this by using the partial fraction method, and if you obtain the expression for this partial fraction, you will see that you can write it as, we can write this simply as a by 1 by minus plus b by 1 minus, and we can conclude, we will see that b will be equal to 2 and a will be equal to 1. Please check these values, and this will be our y of z, this is y of z, then y of z will be finally equal to, just using the partial fraction method for this, we can get the values like, I hope I'm doing it right, so this will be 1 by inverse plus, I hope I'm right. Please check the values yourself. And b is minus 1. I think b is minus 2. And b is minus 2. Please check the values yourself. Or let's do it. Let's solve it. Let's solve it here. Let's solve it from this point. Let's see the answer. So using the procedure of this partial fraction method, I'll say y of z is simply 2 by 1 minus 1 by 2 z inverse. You can write it as a divided by 1 by 1 minus 2 z inverse plus b by 1 minus z inverse. So this is equal to this, and we have written it from this formula: 1 by 1 minus 2 z inverse and 1 by 1 minus z. So this is equal to, now when you multiply this numerator and denominator by this term, you will get 2 is equal to a into 1 by 1 minus z inverse plus b into, no, sorry, this is this should be this should be 1 minus z inverse, and we can, this should be 1 by 1 by 2. Now to get the values of a and b, we force the z equal to 1 by 2 and this z equal to 1. So to get the value of a, first let me write z is equal to 2. So if z is equal to 2, sorry, z inverse is equal to 1 by 2, then z, let me write, if z is 1 by, so put it here, so this is 1 by 2 like this. So if I put z equal to 1 by 2, then z inverse will be 2. So if I say z inverse is 2, then this and this cancels, b's term is gone, so this will be a into 1 minus 2. So this is equal to minus, a is equal to minus 2. So a will be equal to minus 2. Now to get the value of b, so this is a. Now to get the value of b, we'll make z inverse equal to 1. When z is inverse is equal to 1, we'll have 2 is equal to, this term is 0, plus b into 1 minus 1 by 2. So we can say b is 1 by 2, half of 1 by 2, and this is 2. So b should be equal to 4. So b is equal to 4. So in this, we please check the values. The calculation is also should be equal to 4. So now we can write this as y of t, which is defined as 2 divided by 1 minus 1 by 2 z inverse and 1 by z inverse like this, which we will try to have written as this one a by 1 minus 1 by 2 z inverse plus b by substituting the value of a and b. This is minus 2 minus 2 minus plus 4 by 1. Please check the values of a and b again. Let's also y of z is, you can write it 4 divided by 1 minus 2 inverse. Please check the values again. So you can write it as 4. Now taking the inverse z transform, in the causal signal, this will be 4, you can, this is 1. So this is 1, u of n, this is 1, and this is n, u of n. And taking u of n common, that means this will be 4, 1 is by n is the 2, and let me take the outside. So this will be 2 into 2 minus 1 by 2 is by n, u of n. So this is the inverse Z transform, or in short, the step response here. So this is the step response of the system, which is described by this difference equation. So the step response of this system, which is described by difference equation, is simply y of n is 2 into 2 minus 1 by 2 which is 2. Yeah. So this is the step response of this system, which is described by this. So in other words, you can use Z transform to obtain the output of the system, which is described by this difference equation. I hope you have understood it. Please go through this one more time at your own places and see your result. Please check the calculations of EMB here. So this is about Z transform. So this concludes the Z transform section.